What's up, everyone? Welcome back to my channel. Sorry for the delay in uploading this video. I spent nearly a month preparing for exams, but now that they're over, I'll have more time to focus on this channel. We've spent 8 episodes mastering functions, loops, and logic. But as your projects grow, writing your program line by line without organized just isn't enough anymore. We are moving away from writing simple scripts to building systems and entering the world of object-oriented programming, or OOP. This is how we organize code at scale. Let's break it down. Before we jump into OOP, let's look at how code is structured in different programming styles. Imperative, line-by-line commands. Simple, but can become messy as programs grow. Procedural, organized into functions. Good for reuse, but data and logic are still separate. Modular programming, code is divided into separate modules or files, each responsible for a specific part of the program. This improves organization and maintainability. MVC, model view, controller separates the application into 3 parts: model, data, view, UI, and controller, logic. This helps manage complex applications, especially in web development. And finally, object-oriented programming, OOP. We group data and logic into objects. This improves structure and makes it easier to control how your code behaves. First, to create a class for your object, you use the class syntax followed by the class name. We use a special function named __init___ to define the initial actions for that object when it is created from this class. The init function will automatically call when you create that class object and provide the variable in init function. Here, we have 2 types of variables in a class. One is the class attribute, which will be the same for all objects of that class. Another is the instance attribute, which will be different for each object depending on how you assign it. We use the self keyword to interact with the variables included in the class object. If you wrap any function inside that class, it turns into a class method. Here, I create a student class, then an __init___ function and another custom function. Next, I create 2 class objects, instances, using the student class and assign different values to each. If you call the wrapped function inside the class object and that function uses an instance attribute, it will use the specific attribute of that object. Here I call that function for these 2 objects and the result is not the same. Finally, I will interact with the class attribute by changing it, and you will see that it changes for all other objects of that class as well. First let call to print the class attribute out first, then assign that variable directly with the class itself. Reprint and the result here. You can use this exact method to change the value of variable inside an object. Next, we will look at the 4 main principles of object-oriented programming, starting with encapsulation. Encapsulation means wrapping data, variables, and methods, functions, together into a single unit, class, and restricting direct access to some parts of the object. The previous example is still considered encapsulation, even though the instance attribute is public. This means it can be accessed from outside the object, while the class still contains methods. However, full encapsulation is achieved when the attributes are private and can only be accessed or modified through methods, without direct interaction from outside. Imagine encapsulation as a capsule or a box. Inside the box, all the data and methods are stored together, and the outside world cannot directly access everything inside. Instead, it can only interact with the box through specific openings or interfaces. This helps protect the data from unwanted changes and ensures that the object is used in a controlled and predictable way. As a result, encapsulation improves code security, maintainability, and readability. We have this example where we make properties private by using a double underscore prefix. In Python, this will internally rename the attribute to prevent it from being accessed directly from outside the object. For example, the attribute is stored with a different name instead of its original one. Here, we have a bank account class with 2 methods. One is the deposit method, which is called using the object and takes a number as input. It then updates the balance attribute of that object. The other is a getter method, which returns the value of the attribute. We can also have setter methods to assign new values to attributes. Next, we create an object and set its initial balance. After that, we call the deposit method to add 500 to the balance. Then, we print the balance using the getter method. You can also see that I commented out 2 incorrect ways to interact with the encapsulated object. If you run them, they will throw errors. The second principle is abstraction, which means hiding complex implementation details and exposing only the necessary features. In Python, there is no built-in abstraction mechanism like in Java, but we can use the ABC module, which stands for Abstract Base Class. This module can be used without any installation. We import ABC, an abstract method, from the ABC module. ABC is used to create an abstract class, and an abstract method ensures that any subclass must override the method it is applied to. In this example, animal is the parent class. We define an abstract method make_sound inside it, while also having a normal method sleep. Next, we create a child class dog by inheriting from animal, and we override the make_sound method. Then, we create another subclass husky that inherits from dog. If we want to reuse a method from the parent class, we can use the super function. It allows us to call methods from the parent class. In this case, husky overrides make_sound but calls the implementation from its parent using super. Finally, we create an object of the lowest level class which is husky and call its methods. The object can access all methods defined in its parent classes. The third principle is inheritance, which may seem similar to abstraction. In fact, abstract classes often rely on inheritance, which is why these two concepts can be confusing. Inheritance allows a class, child or subclass, to reuse properties and methods from another class, parent or superclass. It also represents an is-a relationship. It can be understood as a way to extend an existing class or reuse methods that are already defined. Continuing with the animal class, it has an eat method. Then, we create a dog class as a child class and add a new method called bark. A child class can also override methods from the parent class to provide its own implementation. Additionally, we can use the super function to call methods from the parent class and extend their behavior. Finally, we create an object and call all the methods defined in both the parent and child classes. Lastly, we have polymorphism, which means many forms. It allows the same method to behave differently depending on the object. In this example, all classes share the same method called makeSound. Even though dog and cat implement this method differently, we can treat them the same way. We create a list of different objects, then loop through them and call the same method. We don't need to know the exact type of each object. As long as the object has the required method, the code will work. This is also an example of polymorphism and duck typing in Python. That was a massive journey into the world of object-oriented programming. We've covered a lot today, so let's do a quick, detailed recap to make sure you've captured everything. First, let's take a look at the evolution of code. We saw how code moved from imperative, where we write line-by-line commands executed directly, to procedural, where we organize logic into functions for reuse, though data and logic remain separate. Next, we advanced to modular programming, splitting our code into independent modules for better management. We even explored MVC, which strictly separates our system into model, view, and controller. And finally, we arrived at OOP, where we group both data and logic into independent objects. This transition allows us to build systems that are organized, scalable, and truly professional. Next, we mastered classes and objects. You learned that a class is the blueprint, while an object is the actual instance. We used the __init___ function to automate the initial setup of our objects. We distinguished between class attributes, shared by everyone, and instance attributes, unique to each object. And we saw how methods, the functions inside our classes, give our objects their unique behaviors using the self keyword. Now, let's quickly recap the 4 pillars of OOP. Encapsulation, like a safe box, we protect our data, ensuring it cannot be accessed directly from the outside. Abstraction, like a TV remote, we hide complex underlying logic, providing only the simple buttons needed to interact with the system. Inheritance, like DNA, child classes inherit the characteristics and behavior of their parent, allowing us to reuse and extend code efficiently. Polymorphism, like a smartphone, one interface can perform many different tasks depending on which app or object we are interacting with. You now have the fundamental tools to build organized, scalable, and professional-level systems in Python. No more messy spaghetti code. If this deep dive into OOP helped you level up your coding game, don't forget to hit the like button and subscribe to my channel so you don't miss the next chapter. Let me know in the comments, which of the 4 pillars was the hardest for you to understand. Happy coding!